One key element of our multiplexers are thin film filters. To guarantee the high quality of our products, we have to characterize those filters individually. If you want to find out how we do it, stick around and we'll check it out. The thin film filters we use basically consist of glass. And the larger ones have a size of 1 square millimeter. Here we have a picture from a microscope, and indeed here on the left side, this little tiny crumb is one of our larger filters we use. If we take a closer look to it, here you can see we have the base material. This means it's the glass. And what makes this glass a filter is this white stripe here. It consists of 100 or even more layers of dielectric material. This means those are layers with a certain thickness and a certain refractive index, and the combination of those layers determines the filter performance. So what does this mean? Let's go here to this whiteboard, and if we take a look on this graphic on the left side, you can see this is a filter. A filter is more or less a reflector for all wavelengths except of one. So this means only lambda 1 is passing. In physics, it's not possible to only have one single wavelength. So this means there is a certain window of wavelengths which can be passed through the filter. And this is even specified in the, for example, CWDM grid. So this passband, the so-called passband, has a width of 14 nanometers. If we take a look on the graphic on the right side, we have the transmission of the filter from 0% to 100%, and on the x-axis we have the wavelength. And if we take a look to the lambda 1, which is this filter, you can see there's a certain passband, a certain window of wavelength which can pass through the filter. So enough for theory. Let's go down to the clean room and see how we actually measure this passband behavior. Now here we are in the clean room, and what you can see is our measurement setup. It's a self-designed station where we can characterize our filters. First of all, we put the filter into a special gripper. It's a gripper which makes sure that the filter is not harmed mechanically. And after that, this gripper is inserted into the measurement apparatus. And what is special to this setup is we're using the actual optics we use in our components. So we have really the information how the filter will perform in our component. After that, there's some optimization, and then we can start the measurement program. It's an automated measurement with an optical spectrum analyzer. And yeah, now here we can see what is the center wavelength and the filter passband. You remember, it's this window of wavelength which pass the filter. And so we can decide if the filter is okay or if it is something we have to remove. I hope you learned something today. If so, please leave a comment and consider following us, and see you in one of the next videos. Bye bye.